Think about the rent on an apartment. It doesn't ride on one thing alone. It depends on the size, and the number of rooms, and how far it sits from the station, and its age, all at once. One straight line, driven by a single feature, can never capture that. With one feature, we already know the story. Plot the points, draw the single best fit line. That was simple regression. One intercept, and one slope. Now add a second feature, and something wonderful happens to the geometry. The line lifts off the page and becomes a plane, floating in 3 dimensions, tilting along to access at once. That plane is the whole idea of this lesson. Here it is in symbols. Our prediction, y hat, is an intercept beta naught, plus beta 1 times the first feature, plus beta 2 times the second, and so on. One weight for each of the p features. Beta naught is the baseline, the prediction when every feature is 0. And each beta j is a slope in its own direction. How much y hat moves when that one feature climbs by 1 unit. One subtle but vital point. This is still called linear, even with many features, because it is linear in the betas, the unknowns we solve for. The features themselves can be anything. Let's live inside that picture, because it makes everything click. Two features, x1 and x2, spread across the floor. The thing we're predicting, y, is the height above it. Every example is a single point floating in space. Now, exactly as the line threaded the two-dimensional cloud, we slide a flat plane through this three-dimensional one. The plane is our model. Its height above any point on the floor is the prediction there, but no plane hits every point. The data is noisy. So for each example, we drop a straight vertical line from the true point down or up to the plane. That gap is the residual, the error the plane makes right there. And here is the whole objective in one sentence. Out of all possible planes, we choose the one that makes these vertical gaps squared and added together as small as they can be. Least squares. Now in 3 dimensions, push to 3 features and beyond. And you can no longer draw it, but the idea holds perfectly. The model becomes a flat sheet, a hyperplane, cutting through a cloud in higher dimensions. More features simply means a higher dimensional fit. Writing out every beta and every feature by hand gets unbearable fast. So we pack the whole dataset into 3 neat objects, and the algebra turns beautiful. First, the design matrix, big X. 1 row per example, 1 column per feature. But notice the very first column is all ones. That column of ones is what carries the intercept. Keep it always. With n examples and p features, X has n rows and p plus 1 columns, the extra one for that intercept term. Next, the target vector, little y, every observed output stacked in a column. And the coefficient vector, beta, the intercept and every slope stacked together. These are the numbers we're hunting for. And now, the reward. Every single prediction, for all n examples at once, collapses into 3 symbols. Y hat equals x beta. One matrix times one vector replaces that entire sum we started with. Check the shapes fit together. X is n by p plus 1. Beta is p plus 1 by 1. The inner dimensions match, and out comes y hat, n by 1. A predicted value for every example. So how do we find the best beta? We write the cost as one clean expression. The squared length of the residual vector, y minus x beta. That single norm is the total of all the squared gaps we saw on the plane. Minimizing it is calculus. Take the gradient with respect to beta, set it to 0, and after the dust settles, you're left with one elegant condition, called the normal equations. If we can invert x transpose x, the solution drops straight out. Beta equals x transpose x, inverse, times x transpose y. This is the closed form answer. The exact best fit coefficients, no searching, no guessing. Watch the shapes make it work. X transpose is p plus 1 by n. Multiply by x and you get x transpose x. A small square matrix, p plus 1 on each side. X transpose y is a matching column. Square times column, beta comes out the right size. And a crucial habit, we never invert x itself. X is usually a tall rectangle with no inverse at all. It is x transpose x, the square one that we invert. And even that only works when the columns of x are linearly independent. Let's grind one all the way through, by hand. Two features and just three tiny examples. When both features are 0, y is 1. Bump x1 to 1, y is 3. Bump x2 instead, y is 4. We want a plane through these 3 points. Step 1. Build x. Each row starts with a 1 for the intercept, then the two feature values. So the rows are 1, 0, 0, then 1, 1, 0, then 1, 0, 1. The outputs stack into y, 1, 3, 4. Step 2. Multiply. X transpose x is a 3 by 3. Its top left entry is 3, because the ones column dotted with itself counts the examples. Fill the rest from the column dot products, and X transpose y comes out 8, 3, 4. Step 3. Solve. X transpose x times beta equals X transpose y is just this little system of 3 equations. 3 beta naught plus beta 1 plus beta 2 is 8. Beta naught plus beta 1 is 3. Beta naught plus beta 2 is 4. From the last two, beta 1 is 3 minus beta naught, and beta 2 is 4 minus beta naught. Slot both into the first equation, and it neatly reduces to beta naught plus 7 equals 8. So beta naught is 1. Back substitute and beta 1 is 2. Beta 2 is 3. There they are. The intercept is 1. The first slope 2. The second slope 3. Our fitted plane is y hat equals 1 plus 2, x1 plus 3 x2. Always verify. Compute x beta and you get back exactly 1, 3, 4. The very y we started with. The plane passes cleanly through all 3 points, so the residuals here are 0. Now what do those slopes actually mean? This is where multiple regression is most often misread. So let's be precise. Take our fitted plane. Beta 1 is 2. That says, if x1 increases by 1 unit, the prediction rises by 2, but only if x2 is held completely fixed. That little condition, holding the other features constant, is everything. People sum it up in 3 words: all else equal, or in Latin, ceteris paribus. It's the promise that each slope isolates one feature's effect, imagining the others frozen in place. And here's the warning that comes with it. When features move together in the real world, bigger apartments usually have more rooms. You can't cleanly change one while pinning the other. Then, a single coefficient, read in isolation, can mislead you, which leads straight to our next danger. This danger has a name: multicollinearity. It strikes when two features are nearly the same information, strongly correlated, almost a copy of each other. Here's the geometry, and it's striking. When x1 and x2 are collinear, the points don't spread across the floor. They crowd onto a single ridge line. Every example lives essentially along one direction, and a plane resting on a single ridge is free to rock. Tilt it steeply toward x1 or steeply toward x2. As long as the two tilts trade off, it still lays right across the same points. The data cannot pin it down. The algebra says exactly the same thing. If one feature is nearly a linear copy of another, the columns of x are almost dependent. So x transpose x is nearly singular. Its determinant creeps towards 0, and inverting it becomes wildly unstable. Watch it in real numbers. Nudge the data by a hair, and beta 1 lurches from 3 down to 2, while beta 2 swings the other way. The individual coefficients are unstable and untrustworthy, even though their sum barely moves. That sum is all the ridge really constrains. The cure is to detect it, drop, or combine the redundant feature, or gently shrink the coefficients. That last idea is called regularization, and it earns a lesson all its own. Two quick but important extras before we finish. First, what if a feature isn't a number, a color, a city, a category? We can't multiply a slope by the word red, so we encode it. Each category becomes its own 0 or 1 column, a dummy or one hot variable, a 1 where that category applies, a 0 everywhere else. Now every feature is numeric again, and the same machinery just works. Second, measuring fit. Planar squared has a sneaky flaw. Adding any feature, even pure noise, can only push it up, never down. So a bloated model always looks better, which is a trap. Adjusted R squared fixes it by charging a penalty for every feature you add. If a new feature doesn't earn its keep, the adjusted score actually falls. It rewards useful features and punishes useless ones. A far fairer yardstick. Your turn, and it tests the one idea people get wrong. A model predicts a price, 3 plus 2 times the number of rooms plus zero point 0.1 times the area. Question: add exactly one more room, keeping the area unchanged. How much does the prediction rise? Pause and think about all else equal. Here's the reasoning. Because the area stays fixed, its whole term is frozen and contributes nothing to the change. Only the room's term moves. Its coefficient is 2 times one extra room. So the prediction rises by exactly 2. Not 2.1, not 2 and a bit. Just the room's coefficient. Because everything else is held equal. If you said 2, you've truly understood it. Trap 1. The big one. Every coefficient assumes all else equal. When features move together, you cannot interpret a single slope in isolation. Trap 2. Never forget the leading column of ones. Drop it, and you force the plane through the origin, which is almost always wrong. Trap 3. Don't try to invert x. It's rectangular. Invert the square x transpose x, and only when its columns are independent, full column rank. Trap 4. Planar squared never drops when you add features. So judge a bigger model by the adjusted R squared instead. And trap 5. Piling on features invites overfitting. The model starts memorizing noise. That bias variance tension is a whole lesson of its own. Let's lock it all in. Multiple regression predicts one output from many features, an intercept plus a weighted sum. Still linear in the betas. Stack the data and it becomes a single clean line. Y hat equals x beta, with that all-ones column carrying the intercept. Solve it in one shot with the normal equations. Beta equals x transpose x inverse, x transpose y, the exact least squares plane or hyperplane, and read each coefficient as one feature's effect, holding the rest fixed. Mind collinearity. Use adjusted R squared, and you can fit and interpret a model in any number of dimensions.